over what Twine is. So it's a unified cluster management system for shared infrastructure. And it's a very robust system. So I guess let's just dive in. Okay. So the table of contents. So the topics that we're going to go over today will be first containers. So really help you understand, because before you even review Twine, it's important to understand what exactly a container is, specifically what's the advantages of that over virtual machines. And then we're going to go over Kubernetes clusters, which is one of the more popular container orchestration cluster management systems. And then we're going to go over Twine. What exactly is it? The advantages, what makes up Twine and its components, and review the performance and evaluation. And then finally conclude. So this picture right here, we're going to go more into it. But essentially what this showcases is, there are many data centers in a region, and each data center holds specific MSBs, and these hold certain rows of these. The row that you see here is essentially, many physical machines, and each of these, if you can see my mouse, each of these right here, borders, consist of a rack, and each rack is basically comprised of physical machines. So from here, this is just some example of, kind of the applications that are hosted on those types of servers, let's say like newsfeed, web, ads. So containers. So really, it's important to understand what containers are. And in order to create these cluster management systems, these lightweight standard units of software need to be set up. And it's essentially that it's packaging code and dependencies together. And the main difference between containers and virtual machines are the fact that there is no overhead in terms of having to create your own guest OS and things like that, or setting up and providing a lot of the memory of your own computing system to provide power to this virtual machine. So when you were, taking OS, things like that, you had to set that up and, use whatever type of virtual machine system with a base guest OS system. But that takes a lot of computing power to run, and it also takes a lot from your original system. So the better method to handle this is to use Docker. And this is the more established container orchestration or container service. And this essentially just over your host operating system and doesn't need another guest OS. And it just runs these applications, and you can basically create your applications from images that you create. And this is basically, let's say you're making let's say a React application or some sort of database application, and you want to make an image out of that, and then from the image you make a container, and that's what these apps represent. Each of these could signify a different container. So definitely a lightweight option compared to virtual machines. They are a lot smaller in size, specifically tens of megabytes in size, and incredibly easy to boot up and shut down. So, whenever you have to shut down a virtual machine, it's quite a lot. And there's definitely been a big move from on-premise servers, because of the fact that, any unforeseen circumstances like disasters can, mess up these servers, and that's it. If you don't have any disaster recovery set up for these servers or backups, then you need something like this to provide those backups and easily facilitate if any type of server goes down, should any unforeseen circumstance happens. And it's also very modular, which is very good for deployments. Okay, so to understand Twine, it is really important to understand Kubernetes. So it's definitely not the most user-friendly kind of application in terms of there's a big learning curve. There's a lot of configuration that goes into something like this. But especially Twine, because it is so robust in what it does, I think Kubernetes, explaining what Kubernetes is and how it does this, how it manages these clusters of containers, it's definitely important to make note of this. So definitely one of the most popular container orchestration tools. It ensures that proper scaling for application workload is possible. It facilitates security. You can run it anywhere. It's very convenient, and it's also provides very quick and streamlined deployments. So this picture right here you see is how the architecture of a Kubernetes cluster works. You would have worker nodes, and these worker nodes will represent your machines, your virtual machines, however you would host it on AWS or things like that. There are services that use Kubernetes like EKS for Elastic Kubernetes services, but essentially you have your machines, which are the worker nodes, and in your worker nodes, you'd have multiple containers that would host your applications. Let it be like websites with a database, everything that makes that website work essentially. So that would be all compromised to one worker node. And then from there, you'd have a master node that essentially dictates and schedules how things happen in terms of which worker node should be set up first. If one goes down, how does these containers go and find another worker node to facilitate the loss of this worker node? So it communicates with these worker nodes through the kubectl, which is an API service, Kubernetes API system that allows you to easily set up your worker nodes and your applications to communicate together. So it's really powerful and also very tricky to set up, but definitely wanted you to see how this setup works in general. Okay, and this is just a more breaking down of how Kubernetes works though. You have the cluster, which is the master node, the worker nodes, all of that compromises the cluster. And so it's basically your master node, which could be a server, but you call it, it has a specific component called the control plane. And this is where all of the scheduling happens, the allocation happens, how much, what tasks should be, what containers should be going to which machines, things like that. So it really controls your deployment. And then you have your worker nodes, which have proxies that allows you to communicate between containers in terms of HTTPS traffic. And each of these containers are also put into these things called pods. So essentially the nodes are your machines, and it can easily be created and removed to easily scale your app. And from there, this cluster talks to whatever cloud provider API you have that you're working with, be it Amazon Web Services, Azure, and things like that, or Google. So this is just a high level overview, and then we're going to go into exactly how Twine is different and how it is better and how it has other advantages for what these systems, what Kubernetes does, so how it's better. Okay, so finally, what is Twine? So it's Facebook's proprietary cluster management system. So it's been running for quite a long time. It actually started back in 2011. So it's been around for pretty much the past decade, and it's rewritten the standards that these modern cluster management systems have basically set and established. And it does this by scaling a single control plane to manage 1 million machines across all data centers. So this bullet point, that's the goal. It actually does not do that just yet. It's something that they're working on, as you saw in the video, that it's moving to a point where they can go to 100% and doing this. But essentially, for the time being, all that Twine is able to do is have a control plane for many clusters or for a region, let's say, because a region can consist of many data centers and each of them can have its own clusters and things like that. So also it moves jobs across clusters, and that's something that Kubernetes does not do. It's really isolated to itself. Going into the limitations of these existing systems, it basically focuses on isolated clusters. These things can't communicate with each other. Jobs can't be run on other clusters, and so you're all dependent on whatever power you gave that cluster, and you can't really help each other out and things like that. So you also do not relay lifecycle management operations in terms of whether or not there's maintenance that happens, whether you start a task, end a task, or a job. There's not much customization. Usually when you create your servers for virtual machines for these containers, for these worker nodes to hold, it's usually very similar to the other one to really facilitate a uniform kind of a setup. So make sure you have enough power to run your applications, because these things are very, very time consuming to set up. So it's a lot of power that needs to be running to get these, especially batch applications like that. So from there, they also do not favor small machines, as the video mentioned. They prefer big machines to handle that workload. And so you need more CPUs and memory to stack that workload. And so it's basically all, Twine is essentially a research project in Facebook engineering. Yeah. So some of the advantages of Twine, as mentioned, is the single control plane that can handle 1 million machines. That's something that they're working on, but for now it's more per region. But Kubernetes only has one control plane per cluster, which was that master node you saw. That has collaborative lifecycle management and host level customization, which essentially allows you to have specific configurations for different servers, different machines, essentially, hardware, OS settings, and specific entitlements. So we'll get into that in a bit, but each host level customization is matched to an entitlement. And also they're very power efficient machines. There's a strong emphasis on power efficiency in a smaller but yet efficient machine, and we're going to go into it in a bit. And the last thing is the shared infrastructure, which is something that is being worked on right now, and it's something that they're moving into, which is called Twshared. Okay, so the design implementation. So you have 12 geo-distributed centers that you saw in the pictures in the video. Each of these regions consists of multiple data centers, and each data center has many main switchboards, which is that MSB I was mentioning. And they have one of the largest fault domains in a DC, and the DC is just data center. So it consists of tens of MSBs, and each of these power tens of rows, which is that row of machines you saw, and the tens of racks of servers, right? So basically the overall definition for a cluster is just a subunit within a data center that makes up 10,000 machines. It's managed by an isolated Twine control plane, right? So for now, it's each region is just for one control plane. And it does this by utilizing a fabric architecture that provides high bandwidth within a DC and across DCs in the region. It's fundamental in allowing the single control plane to manage jobs across the data centers. And that fabric architecture, that's a new technology that is being set up in Facebook engineering as well. So it's a technology that they have adopted into this program to make it even more efficient. So really, it's really tying into that small machines proposal that they did. And that's how it uses that, provides that uniform framework or network connectivity across the containers to really set up that fabric architecture. But we can be for a long time if we go over that also. But yeah, essentially this picture shows the region. Each data center has main switchboards, and each main switchboard has rows, and each row has a rack, and then you have your machines. And there could be multiple machines, but usually it's around 4 or so, but it depends. Okay, so I definitely wanted to showcase and show you guys the layout of the ecosystem. So if you remember seeing the Kubernetes architecture, a lot more simpler than this, right? So you have a lot of components to make this efficient. And that's what they see every time they've been setting this up since 2011. It kind of only started from a scheduler, an allocator, things like that. But then over time, they see pitfalls and limitations, and then they create new components such as the resource broker and the health check service, which are very important in terms of how to understand how your machines are doing. But essentially, the application level schedule at the top is just whatever applications you have to use Twine, communicate through an API, which is the request resources through the front end. That's what the front end stands for. It's just an API that allows you to communicate with the scheduler. So the region gets information, and then it provides information to that scheduler, and that scheduler figures out, okay, I need to figure out what machines can handle this workload. So it talks to the agent that you see here, and it determines what tasks are available, what machines are available to do this. And before it does this, before it assigns anything, it has to talk to the allocator, and the allocator makes sure that every machine that is in this region, in this data center, is healthy. It is not down, nothing is corrupted, things like that. And it does this by verifying with the health check service. And the health check service feeds its data to this thing called the resource broker. The resource broker. And that basically stores all the machine capacity and the machine information, physical machine information of all the machines that are in this data center to determine, what best machines to use for this job. And from there, the allocator understands what to do. So that's kind of how everything talks to each other in a nutshell. These work hand in hand, but they're not as important for the time being. But yeah, and this task controller we'll get into in a bit as well. Yeah. Okay, so entitlements. The way Twine is different from everything else that came before it is really these entitlements. And it's a pseudo cluster that uses a set of dynamically allocated machines to host jobs. So it's essentially just saying that an entitlement is like, I am given a certain amount of machines to do what I want with it, like to perform a job or things like that. So it's a quota for how many machines is needed by a business unit. And that could be for whatever, given a certain budget, things like that. So Twine binds the job to an entitlement rather than a physical cluster. And in this case, it's a job can refer to an application or instances of an application or a container. An entitlement can consist of machines from different data centers in a region. As you mentioned in the video, this can be very important in terms of adjusting like a machine to another entitlement, and that's how it's able to scale. So it's important in providing that fault tolerance. In the previous presentation, we saw that there was, I believe it was partial partitions or some fault that was happening where the zookeeper policy, you would lose, one server would go down or the leader would go down, and then who becomes the leader in that case? So in terms of preventing that and preventing anything in terms of power shutdown or any unforeseen circumstances, there has to be a good amount of fault tolerance. So it also helps automate job movements across clusters, as I just mentioned. And this picture showcases just how much, like, let's say the machines allocated to an entitlement are about 3. And then you want to start a job that has a specific, machine, let's say machine 7 here. So you assign it a free machine, which it has now, and now that job can keep running. And now it's only 2 left. And then if, let's say, job E starts, but now it has more power that it needs to compute, and you need another machine to fulfill that job, then it needs another machine, as you see here, and now you're down to 1. And if not, once it's done, you can stop it, and then you free up the machines, and then that machine can be free to be used by any other application or job. Okay, so the allocator. So each data center has an instance of the resource broker, as I mentioned, which saves all the information about what machines are available, things like that, the health status and everything. And what it does is it reads it and maintains an in-memory write-through cache for reference. And from there, it performs job allocation. And that's only happening when a new job starts and an existing job changes size, or if a machine fails. So in order for this to happen, though, it needs to have this entitlement ID, because it needs to know what machines belong to what entitlement, and it needs to know like what kind of allocation policy, how things should be allocated specifically. There's always certain rules, and this can be kind of in terms of how you have in, let's say, in AWS, your scaling, load balancing kind of thing, and it's all depending on that. And there's a per task map of which tasks need to be allocated or freed. So how does it do this? As mentioned, it just uses that index of machine information, and it partitions the machines with different bins, and then it figures out, okay, now that I have them in bins, now I can allocate tasks to them. So it uses the fault domain as the machine property. And from what I'm understanding, a fault domain is, if you're looking at a physical server or a rack, it's all the components of a rack that, maintain those servers and how they connect to an external entry point to other servers, let's say. That would be the whole fault domain. I may be wrong, but yeah. And it does this also by scheduler. The scheduler is the control plane, as you saw in Kubernetes. The master node was the control plane, but in this case, it's the scheduler. So this is what manages the life cycle of all the jobs and the tasks. It really is what drives Twine components across in response to different lifecycle events like hardware failures, maintenance operations, power capping, and it basically the health service detects failures, creates an unavailability event in the resource broker, and that tells the allocator and scheduler. And from there, the scheduler disables the affected task. And if a job is affected, if it had tasks running on the machine, if an impacted job had a task controller, and we're going to get to that in a sec, the scheduler will inform this task controller of the affected task. And once it knows that these tasks have been moved, then the scheduler requests the allocator to deallocate those tasks, and then I can, allocate new instances of the task on other machines. And that's how it, communicates all together to provide this really efficient system. So it instructs agents to start the new tasks accordingly. And finally, the schedule enables the task so that clients can start sending traffic to them. But it's probably one of the most important things. And we're going to get into also, if this thing fails, there can be a catastrophic failure in many sections of the application. Okay, so the task controller I just mentioned, that is what allows these applications to communicate with Twine. The other applications, like let's say the batch applications or machine learning, let's say, it decides which task operations to proceed and which to postpone, essentially. If an upcoming software release is happening or a maintenance event occurs, then it needs to tell these machines and it needs to tell these the jobs to stop or essentially shut them down. And once this deadline is reached, the scheduler stops these remaining tasks and then allows the maintenance to proceed. Before that deadline, the task controller has three options, essentially. Move the task to other machines, stop the task on the current machine, and restart them after the maintenance completes, or it just does nothing. But in this example, you see how it facilitates this flow, that if you're requesting task 1 and 0 to be done, then all the task controller does is, sends acknowledgements to whether or not it's, and it does this by checking a lot of other setups, of course, to see what it can actually do with this. And from there, it fulfills it. If it's completed, then I can do an acknowledgement to do T0, and then we're fine. In this case, just as the video mentioned, everything is broken up into entitlements, but on top of these entitlements are these things called shards. And this was probably mentioned in the previous presentation, but it essentially is partitioning your entitlement into different sections, or just essentially partitioning or separating it out just to get more reliability and efficiency in that. So here it's just showing how this scheduler facilitates the task controller to acknowledge certain tasks, whether or not if one job is present in another, then it can't run, and then it goes in that order. So if they overlap, then you can't acknowledge them, you can't schedule them. So that's some of the ways it's efficient in what it does. Okay, and host profiles. So this is a very crucial part of how Twine is efficient in terms of how to configure the machine settings, the kernel settings, all the different types of settings for the machines to make it more efficient for what it needs to do. And this can vary for whatever kind of tasks you have going on. So that's why if you are, of course, making a really heavy application, then you don't want to use too much computing power, right? You want to just use a smaller machine or things like that, or different settings to not use so much energies, but that's how this goes into hand. So host profiles are a framework to control host level customizations on entitlements. An entitlement is associated with one host profile per budge constraints and business priorities. So all machines in the entitlement share the same host profile, and when a machine is reassigned from one entitlement to another component called Sidekick automatically applies the target entitlement's host profile. So it knows exactly, like if you have a specific job assigned to a entitlement or a machine, then you know, okay, this machine has specific host profile, things like that, because it belongs to this entitlement. So that's how it knows and how it efficiently allocates what it needs to do in terms of facilitating this process. And yeah, just to mention, it facilitates the settings of kernel versions you can edit, sysctls, modifies the attributes of the system kernel, huge pages, kernel scheduler settings, and CPU controller, as well as storage. Here's just an example of how it configures this entitlement, or each entitlement here has different settings. So the kernel is 5.6, kernel is 5.2 here, and this is handling huge pages, and this is doing something else. So each of them has another way of handling a workload. And yeah, huge pages is also very important in terms of how to do page allocating, reading from RAM. And so now we're going into why essentially they're using small machines and the autoscaling. So all the time when you're doing these types of cluster management systems, you want to make sure that you have a lot of power and you have the computing power to do it as well. But a lot of times you might have way too much computing power and you just don't even use the full CPU to its limit, and you're essentially wasting energy. And that's when this becomes an option to make this more efficient. And that's where they see that smaller machines are better in terms of handling, specifically facilitating the fabric architecture, as well as not using as much energy and being efficient in terms of what power is being, computing power is being used. Because if you're not using the computing power, then what's the point? You're actually wasting money and resources powering those. So they're all usually packed. So about 4 machines that are packed into one sled, and they all share one multi-host NIC, and that's just the network interface controller, which allows it to connect with different servers. So these big machines use dual CPUs, or about that much RAM, but the other ones use only about, I believe, 64 and 18 core CPU. But yeah, it led to about 18% savings in power. And it's also really good in terms of auto scaling to free up these underutilized machines. And so sharding and scaling. So sharding, as I mentioned, is just another way of them providing a way to facilitate these entitlements, so that if one goes down or something, these machines somehow go down, then these shards can have, each shard has a replica, and this replica allows it to, let's say, if it goes down, the second replica can take its place and then do the next entitlement or run what it needs to do for whatever these entitlements have been allocated to do. But you can shard a scheduler by entitlement. So the scheduler is of course sharded because that's probably one of the most important, because it is the control plane. If that goes down, then almost everything goes down. And that's how they facilitated that it is fault tolerant. So it avoids the Kubernetes centralized architecture that usually relies on one central API server and one persistent store. And that's why you saw that there's a bottleneck that it only around cluster or can only handle about 5,000 nodes. So that all these components right here you see here could be sharded. And that's because it also wants to make sure that these components don't, go down. If they do go down, then we have that way to bring them back. So the separation of allocation and optimization responsibilities helps the allocator scale. And the separation of responsibilities between Twine and these application level schedules that you saw, like batch applications that communicate with Twine, they all run separately. You don't want them to connect with each other too much and have Twine do too much on that regard. So this is also another way that it does scaling. Okay, so so this kind of cluster management using one large cluster to manage a region, it's not exactly new. Maybe they're doing a better job now, but Kubernetes has had that happen in terms of using this thing called Kubernetes Federation, which it allows a job to be split across multiple static clusters. And this allows these clusters to communicate with each other. However, it still has that issue that it is static, that once your cluster has just machines to it, it can't be really dynamically stat, and you can't have like jobs going across clusters. So it's really whatever you have is whatever you have. You don't have host profiles to adjust, and but they have been starting to do it. And so Twine dynamically moves machines in and out of entitlements. So here you see how federation works, and every time, let's say task B starts getting more, as you see here, task B. If you see that it's getting more computing power, that it needs more to run and finish the job, then it essentially needs to run another cluster. So it moves over, and that's a good feature. But sometimes it can, put something heavy on this cluster. In this regard, using a resource broker, it figures out, okay, then I can just usually stack these jobs, and this goes hand in hand with the service later on for the shared architecture, because stacking these tasks is what allows it to be more efficient. But that's the way the sharding approach works, adding more scenes to this entitlement. Okay, so the risks. As I mentioned before, if the control plane, the scheduler for a certain region goes down, then this can be very problematic. It can impact almost all the jobs in the region, not just one, and not just instead of just a cluster. There's many clusters to a region. There could be network partitions that result in a regional Twine scheduler unable to manage an isolated DC. And it goes around this by having the principles of everything needs to be sharded, needs to be replicated. The task should keep running. There should be prevention for these kind of destructive operations where the control plane goes down. So there should be fail-safe mechanisms. There's network redundancy. Operational principles is that it can manage itself. It manages its own dependencies. And it has gradual software releases. So it does this over the many data centers of the region over time. So it does it very slowly, but that's the best way to do this without having too much errors. So they're very cautious about that. And it's also a recurring large-scale failure test, just so it knows that this is something that's reliable. Okay, and so the performance and overall evaluation. So everything you saw before, to see it put to practice, let's say Facebook, how it's hosted. The web tier, they tried here to use the Twine system to see how it can facilitate these CPU spikes. And so what Twine sees is that, or the allocator is, and understands that now I have a recommended job size given whatever I get information from these API schedulers from the beginning, right? The let's say batch applications or whatever. It tells the scheduler, hey, I have this kind of job and I need to use machines for it, right? So Twine understands, okay, I probably recommend what you see in the green here. And every time the real job size is always beneath that. So you can see that it is in fact efficiently allocating where these things need to be done efficiently, or which machines to do it efficiently. And this is around the CPU utilization of the web tier. So it lines up very, very well with how this setup is. So in terms of how it's auto scaling, it's really impressive. And for host profiles, you see here, it has improved the throughput of meme cache. And I believe this was type of, off the top of my head now, I forgot what meme cache was. But for this type of application, you can always adjust the type of host profile. So here you would have CPU affinity where you would add more processes to your CPU. And that would be the one change from the original setup. And then here you would change your BPF CFG, or here you would change the kernel configuration settings. And you see here that as you're adjusting these and you're doing more to it, then you have a greater improvement over the baseline, right? 10.2%. And just by adjusting the host profile. So now you see exactly how it becomes more efficient to have these host profiles given the kind of workload you're working with. And here, so just as mentioned in the video, regarding using smaller machines, it's really important to make use of that computing power. And there are some pitfalls to using smaller machines, but overall it has bigger savings. So here you see that this calculation, or this percent, is a calculation of a number of small machines over the how many times greater the TCO, or total cost ownership, of a big machine is compared to a small machine. That's probably a lot to give you guys right now, but essentially the smaller the number is, the more savings. But as you see here, you have more configuration and or less configuration. That's why you see that it's less, more power is needed, or sorry, more configuration than more power. So that's why you see less energy savings. But the less configuration, probably the better, and that makes sense. And for here, host profile switching again, you would see that one of the settings that we have for Twine is that you can use these specific settings called CPU turbo boost, where you can really maximize the performance of your CPU, and that increases lowers the time of processing. And if you're, let's say, doing huge pages of how you're paging a table in memory, that huge pages in itself is already a good way of preventing page faults. And even then, this system can have issues. So there's different ways of getting more. So they started with huge pages, and then they got the CPU turbo boost. So there's many different features they're looking to increase the efficiency of these cluster management systems. So it's things that they look up over time and they improve over time. Sorry. So Twshared. So regarding the shared infrastructure, this is exactly how it's being done. Where you saw in the beginning, Kubernetes has one cluster, or let's say clusters, and all these clusters can be in just one private pool that's specifically for one purpose and that purpose alone. But what happens if you had a shared infrastructure pool where you can share resources and things like that, then that's where Twshard comes into play. And this provides efficient scaling by reducing hardware development and operational costs. So it does this by doing a capacity buffer consolidation, which is it gathers all these siloed buffers and converts them to centralized buffers. And from there, also turbo boost, as mentioned in the earlier example, that's one of the features of Twshard. It makes use of the processor cores and allows the rebalancer to mitigate any power hotspots and issues. And of course, it also has auto scaling to make sure it can use every form of that CPU as much as it can. So here you see that compared to the private pool, it is in fact always coming out on the top in terms of how it efficiently uses the CPU, because you don't want something that just, doesn't use your CPU to its potential. You want it to make use of all the power that it can do. And although it's only 40%, that's probably a good idea in terms of not making these things probably heat up too much. Yeah, essentially overall, they're more efficient in terms of how they use the CPU and memory utilization. And so that's very crucial in how these cluster management systems are more efficient at what they do compared to existing systems like Kubernetes that are really more to isolated clusters and are not even geared towards something like this level of like that Facebook would need. It's more of a smaller type of corporate type of project or data center, but yeah, this is where Twine really comes into play. So conclusion and some of the challenges is there could be entitlement fragmentation and quota fragmentation in terms of they can lead to small entitlements. There could be split up in entitlements that some machines could be allocated to where they're not needed. So that's where you would get small entitlements. Some host customizations could become blockers or barriers for fleet-wide optimization. So essentially one host profile could be good for one pool or one cluster, and it could be bad for another. So that's something they have to play around with. And it's pretty hard to support global services to handle this global infrastructure, to basically handle global jobs across different data centers, things like that. And since small machines are not the industry standard, right? Everyone's using really high-powered machines. Greater cooperation with hardware vendors is needed. So there's a lot more collaboration and fine-tuning to go with that. And there's identified existing cluster management system pitfalls is also something that needs to be done in supporting large-scale infrastructure. And overall, Twine's infrastructure shows these strategies around the limitations as seen by the past, by existing Kubernetes services or existing cloud infrastructure providers. And it's shown that it's efficient by the test that you saw before through the use of host profiles, smaller machines versus bigger machines, one control plane, and a shared infrastructure. And questions?